Presented by Caltech.
Good evening. Thank you so much. It's my great pleasure to introduce Paul Weissman. Paul is now a senior scientist at the Planetary Science Institute, but he spent 41 years at JPL, living as a senior research scientist. And we overlapped for about 20 of those 41 years. Paul did his undergraduate work at Cornell. Then he did 2 masters, one in astronomy at the University of Massachusetts, and one in planetary and space physics at UCLA. He then went on to do his PhD at UCLA. And his first job at JPL, actually back in 1974, was in a group called Advanced Projects Group. And they designed trajectories for future missions. So they used to have this motto that it was anybody, anytime. Paul then became a co-investigator on the Galileo mission, working with the NIMS near-infrared mapping spectrometer instrument. And that's where we overlapped when I came in as a young scientist and also became a science coordinator for NIMS. He then went on, his real love is comets, and he went on to try to join the team of 2 comet missions, which unfortunately got canceled. One was the Comet Rendezvous asteroid flyby, or CRAF, and the other was Champollion, which was going to be a Rosetta lander. But he did end up getting his Comet mission, so he is an interdisciplinary scientist on Rosetta. He has published very widely, over 130 refereed papers, a children's book, edited Planetary Science Encyclopedia, and has written a number of popular science articles. So with that, I'll leave it to Paul to take us on this wild journey to a comet. Paul.
Thank you very much, Rosalie. Thank you all for coming. What I'd like to do is tell you about what I think is one of the best science missions that have ever been flown, and that's Rosetta. It's a mission from the European Space Agency, and it has participation by NASA. So NASA supplied 3 instruments, and it also supplied me. And the idea of Rosetta is to go to a comet. This is our comet called Churyumov-Gerasimenko. It was discovered by 2 Russians around 1967, so they got their names on the comet. And instead of just flying by the comet, as we've done in the past, we rendezvoused with the comet and went into orbit. Okay, so we're spending over 2 years at the comet studying it in detail. And we rendezvoused out near the orbit of Jupiter, so the comet was very quiescent then, it was very dormant, it didn't have a lot of activity. As the comet got closer and closer to the sun, activity began as water ice began to sublimate and other volatile gases and dust. And we just went through perihelion 2 months ago on August 13th. That's our closest point to the sun, and we were about 1.25 astronomical units from the sun. Astronomical unit is the distance between the Earth and the sun, and we passed about 25% further away from the sun. We also deployed a lander in November of last year that landed on the surface and had a kind of interesting tail after it did that. But let me go on and talk about why we study comets first. This is a picture of the solar system. You have 4 terrestrial planets, Mercury, Venus, Earth, and Mars. You have 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. And we've studied all of these planets with missions, but the problem is all of these planets are chemically differentiated. What that means, at one time the Earth and the other terrestrial planets were completely molten, and the heavier elements like iron and nickel fell to the center to form the core of the Earth, and the lighter elements, basically rock, silicate materials, formed the mantle over the around the core. So if we want to find out how these planets formed, we can't find the evidence because everything's been melted. Okay. Same thing for the giant planets. They've been differentiated. All the solid material has gone to the center, and they are surrounded by big gaseous envelopes of hydrogen and helium, much like the composition of the sun. And so when we study them, we're again studying something that has evolved since the formation of the solar system. What we have learned from about 50 or 60 years of space exploration is that the secret to the origin of the solar system lies not in these big bodies or in their satellites, which are also very processed, but in small bodies, particularly the asteroid belt, the Kuiper belt, which is material beyond Neptune that never formed into a planet, and the Oort cloud, which is a giant cloud of comets surrounding our solar system. And when we see long period comets, that's where they're coming from. Short period comets, we believe, come from the Kuiper belt, and the asteroid belt delivers to us meteorites. Meteorites are very good samples of the solar system, very close to the formation time, but they also have been processed to some extent. And even the most primitive of these objects at one time was heated enough to have liquid water in its interior. And that the presence of water, of course, causes chemical reactions and processes it. So we have learned a lot from asteroids about the early chronology of the solar system, but it's the comets, which have been kept so far away at 30 astronomical units or more, which really preserve a record of how the solar system formed. And what we're doing with the Rosetta is unraveling that record. Here's a picture of artist's conception of the early solar nebula. Most of the material is falling inward towards the center and forms the sun, but some material goes into orbit because the cloud out of which the solar system formed had some amount of angular momentum, and it forms a disk of material around the sun, around the young sun. And in this disk of material, tiny particles of ice and dust can come together and grow to form larger bodies. In this case, these are kind of like the early cometary nuclei that we'll be talking about tonight. They're a few kilometers in size, but as these things grow, they form larger and larger bodies and all of the major planets. This is actually seen, these are space telescope pictures of young protostars that are forming solar systems right now. And what you can see, let me go with this one, for example, this is the young star is in the middle, but it's occulted by this disk of material which we're seeing edge on. And that disk is where the planets are going to form in this solar system. These big outflows are because the young star is very active and can blow away the nebula above and below them, but not the ring of material. And all of these are exhibiting the same kind of behavior. There's a young star there, and there's an opaque disk of material around that star where planets are going to grow. Okay, let's talk about comets. This is Comet Hale Bopp in 1997. This was the last really bright naked eye comet. You could stand outside this building, and I did it, look up in the sky and easily pick out the comet. I took my mother up into the mountains to see the comet, and she asked me while we're going down the 210, are we going to be able to see it? And I pointed through the windshield and I said, yes, that's it, right in front of me. So this was a wonderful comet. It was very active. We managed to discover it far out in the solar system, and so followed it around and learned a great deal more about comets. What we know about comets is that the origin of all the activity is called the nucleus. In the case of Hale Bopp, we thought the nucleus was maybe 30 kilometers in diameter, or about 20 miles. And that's a solid body composed of silicates, rock, organics, chemicals, and water and other ices that can condense in the solar nebula where it's very cold. That means out beyond the orbits of the terrestrial planets, out to where the giant planets were forming. But we can't see the nucleus. It's too small, and it's surrounded by this very bright atmosphere of the comet called the coma, which is the freely outflowing dust and gas from the nucleus. The main activity is that the water ice in the nucleus sublimates as it gets close to the sun. That means it goes directly from solid to a vapor, and as the gas expands, it carries with it fine particles of dust that are embedded in the ice. So if we could get a sample of that, it would really be great for us to learn much more about what the original composition of the solar nebula was. The material that flows off the nucleus, this is about, by the way, in this picture, this is about 100,000 kilometers across, about 62,000 miles. It's one of the largest things you can actually see in the solar system, and because of the fact that it comes close, they can be very brilliant objects. The dust coming off the comet gets blown back into a tail by solar radiation pressure. The particles are so small and so fine, they're kind of like cigarette smoke, that the sun shining on them can literally blow them backwards and actually out of the solar system. On the other hand, there's this tail, which is the molecules coming off the comet, and it's called an ion tail because these molecules get ionized, they lose an electron or gain one, and they get caught up in the magnetic field of the solar wind, and they cause this streaming tail, beautiful tail, which the blue light comes from carbon monoxide, dioxide, I never remember which, but it comes from those, one of those molecules, but in fact, a lot of the molecules in the tail are simply water molecules, again, that have ionized by the solar wind. So here's this beautiful phenomena, but as I said, what we really want to know about is the nucleus. This is material, again, that accreted in the early solar nebula 4.56 billion years ago and has been relatively unmodified. This is the nucleus of Halleys Comet, first imaged in 1986. And to give you some scale, this is about 16 kilometers long and about 8 kilometers across, about 10 by 5 miles. This is another comet. We had a flyby mission called Borrelli, and this is about 8 kilometers long by about 3 kilometers wide. By the way, I speak metric, so for those who don't do so, a kilometer is about 0.6 of a mile, a meter is about 3 1/3 feet, and a kilogram is 2.2 pounds. So there'll be a quiz afterwards, and we'll see how well you're all doing. What always gets me about this collection of photographs is all of these comets look very different. Okay, some of it is that the resolution, the sharpness of the images is different. Some of it is that they were taken at different flyby speeds. But the topography, for instance, this is Ville 2 with these large flat basins on it. We don't see that on other comets. This is Tempel 1 with what looks like 2 impact craters. That's the only time we've ever seen impact craters on a comet. But the topography is very different, and so we really don't need just one mission to a comet or 2 missions. We need lots of them. Remember to call your congressman and tell him that. But another thing about these missions is that these are flybys, and they're fast flybys because the comets have eccentric orbits and they're moving kind of fast. And they're just a snapshot in time of what the comet looks like. So all the data in one of these missions is typically taken within about a day of the encounter. And literally, it's the last hour or two where we really learn about the comet. Let me give you an example of how this works. Let's imagine we're driving down the 210 freeway and we want to get a look at Pasadena. Pasadena is about the same size as one of these cometary nuclei. And we're going to do it at the slowest of any of these flybys, field 2, 6 kilometers a second, 4 miles per second. Okay, Pasadena is going to go by real fast. So one of the things we do to improve our chances is we go far away so that we can watch it go by and slew our cameras in time to catch as much as possible. In fact, we get a lot of our information while we're on the approach to Pasadena, because at that point it's sort of sitting in front of us, and it's growing in our camera images, and we can see a few things. We might see the Rose Bowl with a resolution of say the best of these flyby spacecraft, about 10 meters. You can see something 10 meters in size, about 33 feet, and so you can't see people, you can't see cars. You probably will see the freeways, and you may see some particularly large buildings. But even this building would only be about 15 pixels across. So you'd see it, but you wouldn't be able to figure out what it was. The Rose Bowl is probably the biggest structure in town. You'd see that. You'd see that there's something different between the center of it, where the field is, and the stands where the patrons are. But again, you really wouldn't be able to figure out very much about what Pasadena is and how it works and what it's made of and so on. But let's do a rendezvous mission now. Instead of going by at kilometers a second, we're keeping station with the comet. And we are literally circling the comet at walking speed. Imagine you get off the freeway now, slow down from 6 kilometers a second, get off the freeway, and just walk around Pasadena. You can map it out in great detail. You can find every building. You can go into every restaurant. Just being there and staying there for a long period of time gives you a far better idea of what Pasadena is going to be like. And so our spacecraft is literally orbiting the comet at less than a meter per second, walking speed. And that is why we're getting so much information from it. And we're going to do that for 2 years. The comet's going to change a lot over that 2 years. We've already been there a year. But we're going to see the whole range of cometary phenomena. This is our spacecraft. This is Rosetta. This is in a test chamber in Europe. And this is the business end of the spacecraft. All of the science instruments are mounted here. This is part of the infrared spectrometer that is taking pictures in 300 different wavelengths. The cameras are over here. These are star trackers that help keep the attitude of the spacecraft correct. Down here is the lander, which you'll see better pictures of later, but it's all folded up and ready for deployment. This is MIRO, this microwave instrument for Rosetta. This was actually built here at JPL. And the PI is Sam Gokas. I hope he's sitting here somewhere. But this is a microwave spectrometer and radiometer, and it too is giving us views of the comet that we've never had before from any other instrument. So there's a variety of instruments here, some that collect dust, some that collect gas. They analyze them. There's an atomic microscope that photographs the particles down to very, very fine scale. Basically everything you'd want to know about a comet is being addressed by one of the 11 instruments on this spacecraft. This is the whole spacecraft in thermal vac. To test the spacecraft and get as close as possible to the conditions it's going to be in, we put it in a big vacuum chamber. We turn on Klieg lights to simulate the sun, and then we test the spacecraft and run sequences on it to see as best as we can how it will work in true vacuum. The deep space is actually a better vacuum than anything we can make on Earth. But This is one of the steps in the process. Obviously, we can't eliminate gravity, so that's something we have to just speculate or estimate that we're doing correctly. But this is a very big part of testing of any spacecraft. Here's the solar panels on Rosetta. It generates 8 kilowatts of electricity, enough to power a few homes. The reason they are so large, that the 8 kilowatts is at 1 astronomical unit, when we send the spacecraft out to the orbit of Jupiter, it's only going to be generating about 300 watts of power. That's not enough power, in fact, to run the whole spacecraft. So during the flight to Churyumov-Gerasimenko, one of the things we had to do was put the spacecraft into hibernation. We turned off everything except for the heaters and an alarm clock, actually 4 alarm clocks. And after 2.5 years completely inactive, the spacecraft woke itself up and started calling home to Earth. Here's the spacecraft ready for launch. Again, the solar panels are all folded up. The lander has its legs folded up here. This is a boom that carries a magnetometer. Everything's neatly packaged to fit inside the launch vehicle. This is just a list of the instruments. You can see this is a very international undertaking. Many European nations contributing to this spacecraft, contributing to the instruments themselves. As I said, one instrument that we make is an ultraviolet spectrometer. Was made by a team up in Boulder, Colorado. Moreau, the microwave spectrometer radiometer made here at JPL. And parts of one of the plasma detectors that's part of the magnetospheric package. These instruments are going to measure the interaction with the solar wind. Here's the lander. Again, a very complex little thing. It's only about the size of a washing machine. And again, it has a variety of instruments, cameras all around, a drill that's to collect samples, drills that go into the surface to also collect samples and measure the strength of the surface. A great range of things. And one of the really cool things is this instrument called Concert. Concert is on the orbiter also. And the orbiter will transmit a radar signal. And at the time it was built, we expected the radar signal to go completely through the comet. And it takes a picture of the inside of the comet, just like a CT scan. You can put together an image of what the inside of the comet looks like. That's why we wanted to actually have 2 landers, because it's much easier to solve the problem if you have 2 landers in 2 different locations and the orbiter constantly sending signals through the nucleus. But this is going to tell us about the interior of the comet, which is a subject that's very near and dear to me, because I had proposed quite a few years ago a theory that comets were going to be rubble piles, that they were going to be smaller icy cometesimals that were stuck together. And we don't have a final answer on that yet. So here's the orbiter being prepared with the lander down in Kourou in French Guiana, which is the European launch site. You can get an idea of the sizes of these objects from the people in the picture. Rosetta itself is about 6 to 7 meters on a side. The lander, as I said, like a small washing machine, not even with the pedestal that most of us buy with them. Oh, and then here's launch in 2004 on an Ariane 5 rocket. The spacecraft had a rather complex trajectory. It flew by the Earth 3 times for gravity assist. It flew by Mars once for gravity assist. It finally got out to the far reaches of space, out beyond Jupiter's orbit, at which point it started matching orbits with the comet. It also flew by 2 asteroids, which was some fun science we did. So here's one of the first pictures taken. This is about 2 months after the spacecraft was woken up. And I have to admit, when I first looked at this picture, I saw this and I said, oh darn, the damn thing's active. It turns out this is not the comet. The comet is this little dot over here inside the circle. And it was indeed inactive at the time. So this is just a globular cluster in the galaxy far, far away, and here's our little friendly cometary nucleus. Well, the comet decided to welcome us because right after we got there, it had an outburst. Here's the comet. It still looks circular, but then the last 2 frames here, you can see a lot of gas and dust coming off the comet. The really great thing about this is at this point in the mission, ground-based telescopes on Earth could not even see the comet. Okay? So here we're learning something about how a comet behaves at very large distance from the sun, about 4 astronomical units, before anything we can do from the ground. That's why going there is a great thing to do. As we got closer, we started to see that we had a very interesting object. So the pictures I showed you before of cometary nuclei, 3 of them were actually 2 objects stuck together. But they're usually stuck together end to end. In this case, the nucleus is two bodies, but they're sitting one on top of the other. And this was a little strange for us. And we had a lot of debate about what to call this. I thought we should call it the Sphinx because it kind of, Rosetta has an Egyptian theme to it, and this kind of looks a little like the Sphinx, but the consensus from the science teams was a rubber ducky. This one's kind of, the comet itself is much bigger than this one, but you get the idea. And even though we try not to, you still can go to a meeting and someone will say, oh, the head is this way and the tail is that way, and so on and so on. But here we also made an interesting discovery. The comet was observed from the ground in 2007 when it was far from the sun and inactive, and we got a rotation period of 12 hours and 45 minutes. Now that we're at the comet, 1 orbit later, the rotation period is 12 hours and 24 minutes. It's changed by 21 minutes. Why is that happening? Because gas and dust are coming off the cometary nucleus, and they are acting like a small rocket motor, changing first the orbit of the comet. We already knew that that happened with comets. But in this case, also changing how fast the comet rotated. Okay, here's the dimensions of the nucleus. The head is about 2.5 kilometers in diameter and sits about 2 kilometers above the body of the duck. The duck itself, the body is about 4 kilometers long and about 3.2 kilometers wide. And it too is about 2.5 kilometers thick. Okay, so here's our unusual object. This is just before Rendezvous. This is one of our best first pictures of the comet. You can see things down to about 2 meters in size in this picture, about 6.5 feet. And what we see is a very complex topography. There was a lot that, there's, again, just like the other comet nuclei I showed you, it's different. Okay? One thing that's similar is these flat-floored basins over here. And those are not impact craters. They are too big. The size distribution of these basins is too big. What we believe these are happening is these are sublimation basins. And basically a little bit of activity starts at the center, and then the walls of the hole or whatever start to expand outward. It's the walls that are active. The debris that can't be carried off the comet falls to the floor, and the floor is inactive, but it's the walls that are actually where the activity is coming from. We also saw something interesting for the first time. This is a pit. It's 200 meters deep, 200 meters wide, and there's quite a few of them on the comet, at least 18, and we have never seen this before on any other comet. So that was a surprise that really contributed to our understanding. This is just another picture early on in the mission. This is the tail of the duck over here. This is the back of the neck. You can see the neck itself is very smooth. It's covered with material that has fallen off this cliff and just settled into the position there. It also has boulders that have fallen off this cliff and settled into position at the center of the neck. But what I want to show you is a close-up And we see these vertical lines, which are fractures due to the temperature change between night and day. The temperature change is on the order of 100 Kelvin. That's the difference between the freezing point of water and the boiling point of water. It's 180 degrees Fahrenheit. And that leads to a lot of cracking. And we believe all these striations here are due to thermal cracking. We see some evidence of it in orthogonal directions at right angles to the cliff. By the way, the cliff is 900 meters high. This is on the head. It's only 2.5 kilometers in diameter. So it's a tremendous feature, but the gravity is very low. So if you were to step off the cliff here, you'd fall 900 meters, and you'd land at about walking speed, 1.5 meters per second. It would take you a couple of hours to fall. So it's kind of safe to explore on comets, except you have to worry about getting blown off. So this is another picture of the nucleus. For those of you who like to see faces on Mars and things like that, I'll just point out that over here is the head of a lion looking that way, and over here is a schnauzer looking to the right. Okay. It's because the human eye is very good at picking out patterns even when they're not there. Okay. And what I wanted to show you is just this section of it's the neck of the comet, and it's covered with small boulders, 2-3 meters in diameter, all about the same size. And what I think is going on here, some of my colleagues agree, is that these little boulders are the original pieces of the comet. You had a lot of similarly sized boulders that formed, and I'll show you some more evidence of that in a minute, that formed in the solar nebula, and then they were very quickly brought together by processes in the nebula. And so these are the basic building blocks of the comet. Meanwhile, as we move closer to the sun, the comet did start to get active. This picture's at about 3.3 astronomical units. It's overexposed for the comet because of the fact that the jets are still very faint, but you can see jets coming out of many different little source regions, a lot of it in the neck. We know the neck is far more active than the rest of the comet. We don't necessarily know why. So one of the great things was as the mission progressed, starting in August of 2014, we could start to get closer and closer because the comet was still pretty dormant and not throwing rocks at us yet. This is the underside of the duck. It's an area called Enhotep. It's all Egyptian names on this comet. But this is a rock, or boulder, let's call it. When I talk about these boulders, I don't mean to imply any composition. We think they're conglomerates of ice, organics, and silicates, very tightly packed together. So this is a rock. It's about 45 meters across, maybe the size of this building. And as we get closer, down to 28 kilometers, we can start to see that even this big rock seems to be composed of a lot of other rocks stuck together. This is what we call in planetary science a rubble pile, and it explains a great deal about asteroids. It also can explain a great deal about comets. Here's one of the most interesting things. This is those pits that I talked about. Here's one big one that we particularly were able to image very well early on. And you notice the wrinkled surface. This was named Goosebump terrain because it's like the goosebumps that may form on your arm or somewhere else. And again, these are 2 to 3 meter diameter boulders. And again, as I said, I think this is the basic building block. You grew these in the solar nebula, and then all of a sudden they were very quickly brought together. There's about 18 of these holes on the comet. This is one where the picture is overexposed, so the surface looks white, even though it's very black. But what you can see is inside the cylindrical hole are jets of activity. The sun is shining on the walls, and the walls are active. So that, again, fits into this idea that these are the start of sublimation basins, and then it all expands out to form those big flat basins you saw. Just another picture of the same area with the first of those holes. And you can see in the surrounding terrain, there's many other places where it appears to be goosebump terrain, where we're looking particularly at cliffs where material can fall away. We are looking at perhaps the interior unprocessed nucleus of the comet. Okay, let's go close. Let's go really close. This is, again, a picture of the underside of the nucleus called Enhotep. Here's that big boulder I pointed out to you. And these are pictures successively closer from different flybys of the spacecraft. So we're first going to focus on this whole area. We're then going to look at a little corner of it, which is down here. And then we're going to look at an even smaller bit of real estate, which is this. This picture is taken from 6 kilometers altitude. It's the best picture taken by the orbiter. It's taken very close to 0 phase. The sun is right behind the camera, and so there's a thing known as the opposition effect. It's the reason the moon gets bright when it's full, that the surface here, right around 0 phase point, is much brighter because there's no shadows, and all the light gets reflected back to you. This, in fact, is the shadow of the spacecraft on the comet from 6 kilometers away. It's not very sharp because we're still relatively far away compared to the size of the comet and the size of the spacecraft, but that's actually, it's close enough, like when you fly in an airplane, you can sometimes see its shadow, and you see a halo around it, which is this opposition effect that I mentioned. We can also see evidence of layering. There's a continuous bunch of steps here that are, the comet has eroded away, but it seems to be different layers. You know, you can see the edge here, and so on. And why it's layered, there's some theories to explain it, but we don't really know yet. That's just a close-up of the area. Okay, we're also looking at the comet with other instruments. This is Virtus, which is an infrared spectrometer from Italy. Up here is pictures of the nucleus taken by Virtus. It's not as sharp as the camera, but it's taking each picture in several hundred wavelengths. So we can learn a lot about the composition of the materials. Here's the head, here's the body below it. In this case, I think this is the tail of the comet, and here's again part of the neck. But down here, these pictures are in visible light. This is infrared light, and so far into the infrared that this is heat coming off the comet. And we can use that to analyze how the comet behaves thermally. One of the interesting things is the neck is hotter than the rest of the comet. And we believe that's one of the reasons that it's more active, is that it actually gets hotter. And the reason it gets hotter is just the same as if you go to the bottom of the Grand Canyon and you look up. Well, you've got huge walls of the Grand Canyon on either side of you, and they radiate the heat of the day back down to you. And what's happening here is that between the head and the body, you're seeing those hot walls that have been heated by the sun, and you're seeing very little clear sky that you can radiate your heat away, so things get hotter. This is another result from the Moreau instrument, the one built here at JPL, and it's measuring temperatures on the comet, on the bottom of the comet, and the highest temperatures are here where the sun is directly overhead in this picture, and the temperatures either way drop down because it's either cooling in the afternoon or still getting warm in the morning. And you get to the edge of the visible comet. This is a model from imaging, and very quickly you see the temperature of cold space. But over here, it doesn't drop off as fast. And what's that's telling us is that there's actually more of the comet that we're not seeing because it's not illuminated. This is towards the south pole of the comet, and when we first got there, the south pole was in complete darkness. So we can use the Moreau instrument making its temperature measurements and learn more about what the actual shape and size of the nucleus is. One of the most important experiments is just measuring the mass of the comet, because we want to find out what the density is. And right here, the mass of the comet turns out to be 10 trillion kilograms, 22 trillion pounds. Kind of heavy, but actually a very small body in the solar system. From the imaging, we can measure the volume of the comet, and then if we divide one number by the other, we get the density. And the density of this comet nucleus, this is the first really precise measurement of a density for a comet, is only 0.5 gram per cubic centimeter. Water ice is 0.9 grams per cubic centimeter. Water is 1 gram per cubic centimeter. So this is a very underdense body. And if we take all the materials that we know are part of a comet and stick them together and pack them really tight, we know that the density of that would be 1.65 grams per cubic centimeter. So if we divide one number, this number, by that number, we find out that the porosity, the amount of empty space inside the nucleus, is 71%. Now, we see that with some asteroids. We see numbers approaching that, never quite this high. But basically, the interior of the nucleus is more empty space than actual material. And there's two ways we can get that. One is called microporosity. If you hold a rock in your hand, it'll have cracks in it. And although the volume of the rock will look larger, those cracks are empty spaces that don't contribute to the density. We also have what we call macroporosity, and that is if you take a box of baseballs, pack them as tightly together as you can, because they're not bricks, because they're not all the same size, there is space between those baseballs in that box. And this can actually be looked at mathematically, and 26% of the box of baseballs is empty space. Now, again, we think Comet is a rubble pile of icy conglomerate pieces. They're stuck together, they're irregular in shape, they're different sizes. So we can start to think about macroporosity giving us a great deal of the explanation for the volume for the low density of the nucleus. There's a wonderful instrument called Rosina, which is from the University of Bern in Switzerland. And these are just some of the chemicals they are measuring coming off the comet. These are very common things like water, carbon monoxide, carbon dioxide. For every 100 water molecules, we see about 20 carbon monoxide molecules, about 6 carbon dioxide molecules, and then about 1%, 1 molecule per 100 water molecules for the formaldehyde and the methanol. These are the major constituents. All of these are very minor constituents, well less than 1%. But there's two interesting things about this. One is if we look at a star-forming region, these are the elements we see there in the cloud where a planet and where a solar system is forming. If we look at interstellar space, we see these molecules. And additionally, if we want life to start on Earth, we need these molecules. Okay, we have to have a mix, not just of water and sand or something like that. We have to have a mix of chemicals that have been pre-made by physical processes, nothing to do with life, but more chemically evolved so that we can, when this stuff comes down, life can actually start on a planet. This is from the atomic force microscope. These are grains of dust the size of interstellar grains. Very small, less than a micron across, a millionth of a meter. This is the Kozak instrument, which is collecting dust and chemically analyzing it. And so this is a fairly large particle. It's about 0.5 millimeter long. But you can see it's made up of a lot more small particles together. So let me quickly go over some other results. One question we always have is, where does the water on the Earth come from? To try and figure that out, we look at something called deuterium-hydrogen ratio. Deuterium is simply heavy hydrogen. It has an extra neutron in the nucleus. And that ratio on the Earth is very well measured in ocean water. but in this comet, it's 3 times that value. So this comet is not a good candidate for the water on the Earth. The current consensus seems to be that it's asteroids in the outer main belt that contributed to water. The water production, as I already said, about half of it comes from the neck. The rest of it is evenly spread around the nucleus. Water ice on the surface is rare, but it does exist. But it evaporates, and there's water frost forming on the surface during the night. It evaporates very quickly at sunrise. The conductivity of the surface is very low. That means you don't have to dig down very far before you see very cold temperatures, which preserve ices, much more volatile ices than water, such as carbon dioxide, carbon monoxide, nitrogen, etc. And then this is combined with the lander. We saw no magnetic field. This is a picture I'd like to show. These are artist conceptions from the European Space Agency of what the lander would encounter. And here's the first one. It showed the comet kind of with a bright surface. We knew that was wrong, actually, at the time. Here's a comet with a rough surface, but at very low scale, so the lander could land in this material. Here's a project manager's nightmare, is trying to land in this this mess of topography. And then this is the final artist conception, and we're going to the beach. A very benign comet, a very friendly landing location. And what actually happened is we did land in a location much like this, and then we bounced into a location much like that. So this is some landing sites that were picked out. We tried to find a landing site that accommodated everyone. The trajectory engineers had specific things they were looking for. The communications engineers had specific things. The site had to be sunlit enough that the batteries on the lander could recharge, and so on and so on. And then we had this meeting in Toulouse, and one by one we rejected them. This site was rejected because just nobody liked it. But this site was accepted because nobody hated it. So here's that site. This is a picture taken from the orbiter from an altitude of 30 kilometers. It's hard to believe, but 77% of that site is flat, soft land, flat land that would provide an excellent landing site for the comet, for the spacecraft. The circle is about 900 meters long. It's actually, the real thing is an ellipse along the trajectory of the spacecraft. But we're going to land on the comet, and we're going to land right next to that rock there. This was 113 meters from the target point after a trip of 6.4 billion miles. So not bad. Here's the day of the release. Here's the orbiter, picture taken from the lander. Here's the lander, picture taken from the orbiter. And what we can tell right away is everything's fine. The legs have deployed. The magnetometer boom has deployed. There's 2 little antennas that might not be able to see for the radar experiment. Everything's hunky-dory. Okay, here's a view. The lander has a camera right on below it that's taking pictures on the way down. And here's a view of the comet from only 3 kilometers altitude. And I'm going to go to a movie. Again, there's from 3 kilometers. The next picture is going to be from 90 feet. 60 meters. Okay, and as we get closer and closer, we get a better and better view of the surface. And this is where the lander is estimated to have struck. What's very interesting is that rock that's under one of the legs, and that may have contributed to the fact that we bounced. The last picture's from 9 meters altitude. Okay, so there's where it is. I'm just going to go back to that picture. The surface looks more like gravel than sand. There's a lot of gravel-sized, centimeter-sized particles. And we've seen this on some asteroids, and we may be seeing the same thing on the comet. Okay, well, what's the orbiter doing as the lander goes down? Here's at 3:14 in the afternoon, the lander is skimming across the surface of the comet. The lander is actually falling vertically, but the comet is rotating underneath it. And so here it is at 3:19 in the afternoon, 3:23 in the afternoon. This is a picture taken earlier where the surface is not yet disturbed, but this is the target point. Here's a picture taken afterwards, and you can see the 3 feet of the lander where it hit, but there's no lander. And if you look around over here, right here next to this cylindrical rock, there's the lander. It's changed directions, and it's bounced back up into the air, back up into the sky. This is actually a picture from the orbiter of the lander. It's very faint, it's very hard to see, but the lander over this large flat basin that's right next to the landing site. This is a reconstructed trajectory. Here's where it hit. It bounced and hit something here, changed direction again, and then landed on this slope on the outside of the basin. It actually bounced pretty high the first time and even higher the second time. And this is where we know it is. We actually have it narrowed down to about 10 by 30 meters in size, but we don't we haven't yet achieved the picture from orbit showing the lander. And this is what the surface of a comet looks like. The lander is in this group of very tall, for want of a better word, Serac-like features. There's a lot of them sticking up here. It's leaning against another one of these. And so one of the legs here we think is resting on the comet. This is one of the antennas from CONSERT. Another leg is also resting on the comet. But the comet is leaning against the wall. And instead of having a surface below it, there's a lot of empty space below it that the instruments cannot reach. And that was a problem. But here we can see very fine-grained material. Here more solid material, but again with a lot of thermal cracks in it. We can also, because the cameras are very sensitive, we can look at other areas around the lander which are very faintly illuminated by scattered light. But again, we can see what the area looks like. Again, thermal cracks in the rocks. 5 of the cameras, there's 7 cameras around the lander. 5 of them are useful. 2 of them are just looking at a blank wall that's not illuminated. And we found out a lot. As I said, Rallis instrument took pictures all the way to the surface. Shiva, which is the panoramic cameras, they were able to look at some areas, even shadowed areas. By stretching the images the same as you do in your computer, we can actually reveal many details. MUPIS and Sensimi are 2 instruments that were pounding probes into the surface, one to measure physical properties, one to measure temperatures. And they each went in a few centimeters, but then they encountered a very hard layer, and much harder than we expected to see on a comet. And one instrument, the hardest it could pound was half a megapascal, the other 5 megapascals. Water ice has a hardness of 12 megapascals. So we think what may have happened is that there's a layer of ice that has formed below the surface, and these 2 instruments can't penetrate it because it's too hard. CONSERT, the radar, detected uniform interior, but only with a resolution as good as 10 meters. That means if there are smaller things inside the comet, CONSERT cannot resolve them. And as I was talking about, the inside of the comet is made up of boulders about 3 meters in size. No intrinsic magnetic field. The sample drill did not encounter the surface. They tried extending it, and it did not encounter a solid surface. Therefore, the 2 evolved gas analyzers measured only the cometary atmosphere, which was still a very valuable measurement because now we're seeing what the composition is right at the surface. It actually evolves very quickly as material flows away from the comet. and the alpha particle experiment did not contact the surface, and it was, it required, it had a switch on the bottom. When it hit the surface, it opened up, so it never opened up. We reacquired the lander in June of this year, but we never got any more science data out of it. It kept sending housekeeping data, but was not working very well, and we could not get commands into it. So what's happening since then? This is just pictures of the nucleus, very active through the summer, and we're continuing to make these measurements. We're continuing to look at the composition of the coma, see if it's changing over time, see if some molecules are coming out that we haven't seen before. We're continuing to analyze dust particles, both counting them and also compositionally analyzing them to see what they're made of. Two interesting things. One is that the comet, as it approached perihelion, which was going to be August 13th, it started having outbursts. And these three pictures were taken in the nucleus 18 minutes apart. So here, everything's pretty quiescent. 18 minutes later, a huge outburst of material, and 18 minutes later, nothing again. This is unexpected, but we are seeing a lot of them. We've seen at least 26 outbursts. And what we know about them is they don't contain any excess of water, but they contain excess of more volatile molecules like carbon dioxide and carbon monoxide and formaldehyde and so on and so on. Up to typically 2.5 times as much as those gases compared to the quiescent comet. Sometimes for hydrogen sulfide, it's 7 times as much as the quiescent comet. We think these may be pockets of volatiles in the comet that as it sublimates, it breaks open and suddenly lets all these gases out. Another theory is that this is caused by a substance called amorphous ice. If you make ice very cold, it's not cubic like your ice cubes in your refrigerator. It's not a crystal. And if you warm that up to about 110 degrees above absolute zero, it suddenly transforms into crystalline ice. And it's an exothermic reaction. It actually gives off energy. So we think these may be places where the amorphous ice deep inside the nucleus is getting exposed and getting warmed up and gets warm enough to cause this reaction. Yeah. This is just an example of one of these outbursts. And you can see there's very little warning of it. There may be a little bit of activity before it, and then suddenly this huge outburst of gas and dust. Here's another one in late August. This is coming off, I think it's the body. I think this is the head down here. So this is coming off the body. We've seen, as I said, about at least 26 of these. Now, the final thing I'll talk about, we're seeing changes on the surface. We know that Comet's losing material, and we're seeing changes, but they're nothing like anything we might have expected. This is, again, that region called Enhotep. This is the base of the bottom of the comet, the bottom of the duct. For reference, look at these two boulders over here and this little cluster of boulders over here. So this is how it looks without any problems. I'm going to go forward to one that can show us the changes. 24 May, everything's normal. 3 June, we start to see a little circle form. 5 June, we see it much better. This wasn't there before, but it's forming, okay? 13 June, it's growing, and another one has started down here. It continues to grow through this sequence. Compare this picture with this picture, because the comet is radically different. The area of this area of the comet is radically different. We think this material is falling, the surface is falling lower. It's about 5 meters difference, about 17 feet difference between here and here. And these grow to the size of those pits that we see on the other side of the comet. And so these may be pits first beginning to form. So at some point, we think this material will collapse, and we'll see, again, a cylindrical pit below it. And it just continues to grow, and even other changes to the surface continue to grow. This is totally mystifying. We do not have a solution to why this is happening yet. So I apologize for going over my time. This is where Rosetta is now. It's approaching the orbit of Mars. It's about 1.5 astronomical units from the sun. We're going to follow it until September 30th of this year, at which point we're going to land the orbiter on the nucleus. Whether we'll be able to get pictures from the surface, I don't know, but we are going to actually dispose of the orbiter by making it a part of the comet it's been studying so long. And this is our own little selfie taken by the lander when it was still attached. Here's one of the solar panels. Here's the comet, active jet coming out of the neck. This is our little corner of the universe. And stay tuned for another year, and we may have a lot more things to show you. Thank you.